The focus of this video is to learn about the 5 common binary compounds that form acids in water. We'll learn how to identify and name them, what happens when they react with water, and how Arrhenius and Brønsted Lowry explain these reactions. Let's begin by identifying the 5 common binary compounds that can form acids when dissolved in water. The compounds include hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide, hydrogen sulfide, sometimes called dihydrogen sulfide. When these compounds are in their pure form, such as solid, liquid, and gas, we name them as regular binary non-acid compounds, just like you see in this column. However, when they are dissolved in water and become aqueous, this symbol right here, as a reminder, is the symbol for aqueous. So, when they are dissolved in water and become aqueous, they are named as acids. So, for example, HF aqueous would be hydrofluoric acid. And the same thing for the rest of them. Now that we know the 5 common binary compounds, let's look at what happens when they react with water. According to Brønsted's Lowry theory, an acid donates a hydrogen ion and a base accepts the hydrogen ion. In these reactions, the acid donates a hydrogen ion to water. Water accepts the hydrogen ion and forms hydronium. What is left from the acid becomes the conjugate base. For example, hydrofluoric acid donates a hydrogen ion to water. Water is the base because it accepts the hydrogen ion. The hydronium that forms is the conjugate acid, and the fluoride that is left is the conjugate base. The same reaction also helps us understand the difference between strong and weak acids. While it is true that strong and weak acids can both donate hydrogen ions, at the end of the day, they have different bond strengths. Strong acids hold on to their hydrogen ions weakly when placed in water, and they donate almost all of their hydrogen ions. In contrast, weak acids hold onto their hydrogen ions more tightly and only donate some of their hydrogen ions. For example, hydrochloric acid is a strong acid, and hydrofluoric acid is a weak acid. Now that we understand what happens when these compounds react with water, let's look at how we name them as acids. To decide whether a compound should be named as one of the 5 common binary acids, we first ask ourselves the following question. Does the binary compound has one of the following states of matter, solid, liquid, or gas, such as the examples in here? If yes, you name it as a normal binary non-acid compound, meaning that you're going to name the first element just like you see it in the periodic table. You're going to name the second element, but change the ending to IDE. Examples include hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide, hydrogen sulfide, also known as dihydrogen sulfide, all while keeping in mind that its state of matter is either solid, liquid, or gas. If the binary compound does not have one of these 3 states of matter, then it's going to have the state of matter of aqueous, AQ, such as the example that you see here, which is hydrobromic acid. At that point, you would name it as a binary acid. And it's going to have the following rule. You write the word hydro plus the root name of the nonmetal plus the suffix ic and the word acid. Examples include hydrofluoric acid, hydrochloric, hydroiodic, hydrobromic, and hydrosulfuric acid. Remember, AQ means the compound is dissolved in water. When dissolved in water, these compounds donate hydrogen ions to water, which accepts the hydrogen ion. This is what makes them acids according to the Brønsted-Lowry theory. Now, let's put everything we have learned together. To summarize the main points from both videos, Arrhenius theory tells us that if we use hydrogen chloride, such as what we see in this example, it will break apart in water and release a hydrogen ion. Brønsted-Lowry theory builds on this by explaining that the hydrogen ion that was released is donated to a molecule of water. Water will accept the hydrogen ion and form hydronium. The remaining chloride is left behind. And that is how the 5 binary compounds become acids in water.